So we are faced with a problem originating from statistical physics of evaluating an integral in a large number of dimensions where apparently the problem is physically intractable. Now let's remind ourselves of what the setting is. So to begin, we are given a function. A function is in one or more dimensions. So we're thinking of a function in, let's say, on the unit interval, or the unit square, the unit cube in 3 dimensions, or more generally, a unit cube in d dimensions. And for regularity's sake, let's say the function is bounded in absolute value. The precise size of the function, the value of the bound, does not matter. We'll keep things simple and say the function is bounded by a unit value. Our objective is to evaluate the integral of the function over its domain, in other words, over the d-dimensional cube. A smidgen of vector notation will simplify our expressions and allow everything to be put together in bite-sized pieces. So let's restate the problem in vector notation. So the idea again, we are given a function, let's say in d dimensions, with variables x1 through xd. Each of these variables takes values in the unit interval. Together, then, the collection of d variables takes values in what we call the d-dimensional unit cube. And the usual notation for this is the unit interval with a superscript d, indicating that we have d variables. Okay. So we are given a function on the d-dimensional unit cube, and the function is bounded in absolute value by unit. What do we need? We want to evaluate an integral. And we will compact the notation for the integral using this vector notation by saying, I want to integrate iteratively over the d variables in the unit cube the function f of a boldface x, which represents the d variables x1 through xd, d of boldface x representing d of x sub d through d of x1. Okay, so here's just a compact way of writing the same integral which we saw on the previous slide. Our objective is to evaluate this, and we've seen that numerically this is going to be very difficult. The idea that was proposed by Fermi, von Neumann, and Ulam was to try a chance-driven computation. Take a gamble, they said. What does that mean? So suppose we start by picking up a collection of d variables by sampling at random from the d-dimensional cube. What does this mean? All right. To put an image firmly in your mind, imagine that you have a 3-dimensional cube. You have 3 variables. You're going to pick a point inside the cube, eeny, meeny, miny, mo, at random, and out comes a value. Of course, you want to do this in a uniform way over the whole cube so that no area is unfairly represented over the other. In other words, we have random sampling according to a uniform distribution. What does this mean? It means that each individual variable, x1, x2, through x sub d, are selected by independent sampling. They constitute repeated independent trials from a common uniform density on the unit interval. Now, this is a setting we well understand. So, if we have repeated independent trials, then the probability log governing the ensemble or the collection is given by a rule of products. You recall, in the discrete domain, probabilities multiply. In the continuous domain, densities multiply. And so, accordingly, what this means formally in notation is that this vector of d variables, boldface x, is governed by a joint density p of boldface x, and we obtain p as a product measure by multiplying out the individual densities. Recall that we had introduced a uniform density, u of x, a function which takes value 1 in the unit interval and 0 outside it. Each of our variables is governed by that self-same density. And so to obtain p of x1 through xd, we simply multiply out the uniform density evaluated at x1 times the uniform density evaluated at x2, and so on. Now, of course, since the uniform density takes value 1 only in the unit interval, this product will be 1 precisely when all the variables individually are in the unit interval. In other words, this product is going to be 1 exactly inside the unit cube and 0 outside it. So this is the uniform density in d dimensions. Now, we've got this random point by random selection. So we understand how we can do this in principle. All we have to do is generate d independent uniform variates and stick together a point in d dimensions. That seems relatively simple, even in 200 dimensions. That's not a hard problem at all. Once you've done that, you've got a random point in the cube. What do we do next? Well, look up the value of the function that is given to us at that randomly selected point. Naturally enough, we want to call the value of the function at that random point, let's call that y. Okay, so y is f of x. Now, the difference here from the normal setting is that this is y evaluated at a random point x. In other words, y itself is a chance variable. Okay, so maybe we should compute things about y. What can we say about y? So, pick a random point x, evaluate the function at that point x. That's one lookup in our lookup table, one computation. This is now a new chance variable, y is equal to f of x. One of the questions we could ask is, well, what is its expectation? What is e of y, or what is the same thing, the expectation of f at a random point x? Now, the change of variable theorem immediately rides to our rescue. How are we going to do this? Pick any generic point, little x, inside the d-dimensional cube. Evaluate the value of the function at the little point, f of little x. Weight this value for the function according to the mass that is placed by p near little x. Integrate out over all possibilities as x sweeps over the d-dimensional cube, and Bob's your uncle. There you go. This is an expression for the expectation of f at a random point x. The student might well object at this point that, well, this is all well and good, but you're giving me another d-dimensional integral, and you already told me that computing a d-dimensional integral is going to be hopeless. So where do we go from here? Well, I'm not actually going to evaluate this integral, but I do want to analyze it and see where it leads us. So, to begin, in principle, in an integral like what you see on the right, the variables x1 through xt, which comprise the vector boldface x, range over all possibilities in your d-dimensional space. But of course, in practice, where they can range is constrained by the density function p of x. Recall, p of x is 1 inside the unit cube and 0 outside. So this big integral collapses into just an integral over the unit cube. There's no contribution from outside the unit cube. And inside the unit cube, p of x is identically 1. And so this integral collapses to a slightly simpler looking integral. Still formidable, but simpler. Pause for a moment and take a look at that expression on the right. Do you recognize it? Of course you do. This is precisely the value j for the integral of the function over the unit cube. This is what we want. Oh, this is brilliant. Understand what we have done here. We selected a point at random. We will evaluated the function value at that point, but that's a chance variable. The expectation of the chance variable is exactly the thing we want to compute, j. But, you know, it's not going to be very satisfactory to just pick out one point and say, oh, evaluate the function here. This is your answer. Why? Because, yes, on average, the answer is going to give you a value j, but it's going to be scattered all over the place. And so naturally, we want to ask, how much is that scatter? How widely spread out around j is it? So naturally enough, we want to take a look at the variance of the value of the function at a random point. We'll have recourse to the change of variable theorem again. Pick a point, little bold-faced x, inside the unit interval, any point. Evaluate the function at that point. That's f of x. Ask how far is f of x from the expectation we've just computed, which is that fixed but unknown j. In other words, look at f of x minus j, and naturally enough, since I don't care whether you're on the right or left of j, we're going to look at the square of this. And so we're looking at the squared deviation of f at a given point x from j. We'll weight it in accordance to the mass that x puts near that point, integrate out of all possibilities, and now we've got a variance. Now, we're going to simplify this quickly, and I'm going to be greedy here, and I'm going to be satisfied with very crude approximations. But to begin, this is a process we've seen before. Right? To try to simplify it, we'll take a look at the integrand, and inside the integral we find that there's a whole square in square brackets, something like an expression of the form a minus b the whole squared, where a is identified with f of x, b with j. Well, we know from elementary school that a minus b the whole squared is inevitably a squared minus 2ab plus b squared. And so we write this down. But the moment we write that down, we realize that I can compute the integral by adding up three contributions, one from the a squared term, one from the minus 2ab term, and one from the b squared term. All right, let's write this down. So the a squared term contributes an integral of the form of f of x squared. The 2ab term contributes, well, since 2ab is identified with 2 times f of x times j, and 2j is a constant, it comes out to the integral, and so I've got 2j times an integral of f. And finally, the last term, b squared, will correspond to a j squared, but that's a constant, fixed but unknown, yeah? But that constant comes out of the integral as well, and that's our third term. We can simplify this quickly. It looks like we're making things worse here by expanding an integral into bigger and bigger and bigger and messier things, but bear with me. Take a good hard look at the integral in the second term on the right. Now, what do you say? Does that remind you of anything? It should. It's exactly the expression for j that we wrote in the previous line. So that entire integral in the middle is exactly the quantity we want to estimate, j. What about the third term on the right? We're integrating a density over the entire range. And densities are properly normalized to a unit. And therefore the integral must be 1. Or if you want, you can identify that p of x is 1 only inside the unit cube. So we are integrating d of x inside the unit cube. We are looking at the volume of the unit cube, which is inevitably 1. So the third term becomes 1. Now we see what happens. The middle term contributes minus 2j times j, or minus 2j squared. The third term contributes plus j squared. Cancel 1j squared, and now we've got a slightly simpler expression. An integral of f of x the whole squared, weighted according to p of x, from which you subtract j squared. A little house cleaning here will make things even simpler. J squared is a positive quantity, whatever it is, and I'm taking away a positive quantity on the right. If I expurgate, eliminate the term j squared, I can only increase the value of the term on the right. And so I've now got an inequality. The variance of x is no more than the integral of the square of f of x, weighted according to p of x. All right, having made one approximation, let's go ahead and make one more and simplify our life even further. What do we know about f of x? Well, we know it's bounded, and we've assumed it's bounded by unit. Therefore, in absolute value, f of x is no more than 1, and therefore the square of f of x is also manifestly no more than 1. F of x the whole squared is less than or equal to 1. If in the integrand I replace f of x squared by 1, I can only increase the size of the integral. And so I've got, this is no more than the integral of just p of x dx. And what is that? Well, I'm integrating a density and therefore by normalization it must inevitably again be unit. What's the moral here? If I select a random point in the d-dimensional cube and evaluate the function at that point, I get a chance-driven variable. But that variable has expectation exactly j, the quantity that I want to determine. And the expected squared spread, the variance of that estimate, is no more than unit. Okay, this sets the stage for a beautiful and elegant resolution of our problem. And this will come up next.